All right, so last week, here we are. I just sent an email out. Well, I always send an email out on these days, but I sent in that email, it detailed the end of the semester, which is also detailed right here. And let me also really erase that since test 3 was returned, right? So I returned test 3, and your grade therefore is complete, except for the bonus homework that's due this evening. And you can see some of the return you could get there. And let me just clarify that one more time, what's up there in case you didn't see that last time. If you have any missing homework, that's really what this bonus homework is for. So I'm going to drop the lowest. I think we had, I don't remember, but I'm going to drop the lowest 10% of the homework. So that's either 2 or 3 homework problems or homework sets. And then if you have any missing gaps in the rest of the homework, I'll take any problems of the 14 that are out there due tonight and add those in to make up for anything that you're missing. If you then have extra problems left over, gosh, I'm just thinking about how long this is going to take me to do. If you have extra problems, I'll then apply those to things like quizzes and tests. That's the way that it's going to work. And it's a 1-to-1 return on homework, but a smaller return on tests and quizzes. And so just to detail the end of the semester, we are now, let's see here. We've completed all of this so far. This is last week. We're now doing Monday. We're going to finish up the notes, right? Might be a little bit of a shorter session like it says there. So you're welcome to start asking some review questions. We could do some of the homework if you're interested in looking at that. And then Wednesday is totally review, 100% review, whatever you want to talk about Wednesday to help you prep for the final, which is Friday. I'll do. So let me just say that again. Friday is the final, in person. It's going to just be kind of during class time. You can take longer if you need, but the idea there, it may not be like a full exam length exam. Usually I write exams for 2 hours. That's what the time period usually is. In these strange COVID times, the school's decided, you know what? We just need to fit them inside a class period. No idea why, but anyway, that's what we're going to do. So it's going to fit inside a class period approximately. So just come to your normal class time on Friday. If you want to arrange a different time, like if you're working or something, let me know last week. So let me know today. Okay. I think that's all I want to say is this sort of an intro. Thoughts about anything you want to talk about? Homework, anything you want to look at before we finish up our notes here?
So the optional homework stuff is due today?
I think
Or
that's
is it
right.
due Wednesday?
I'm sorry, Wednesday. Yeah, it's Wednesday. I'm sorry.
Okay.
Yeah, thank you for clarifying. For some reason, I had in my head that today was Wednesday. It's due on Wednesday. Yeah, thanks for clarifying that. I'll just say that one more time in case anyone else missed that. The homework's due on Wednesday. For some reason in my head, I was thinking it was Wednesday. I don't know why. Other thoughts or questions? So, there's also an opportunity to ask questions about it on Wednesday too. That's what that means as well. Anything at all? I'll just mention one more time for the final exam. It's in the email I sent out today, so check your email if you're not. I'm just doing a test on test 1s, 2, and 3. And so the past, topics and practice problems and things like that apply for the final. And you can bring 3 note cards in. I was sort of thinking like if you just brought your note cards from the 3 tests in, you'd be all set. If you want to like make a page, a normal size page, that'd be fine too. I see Rashid's telling me something about some error. Can you send me an email about that? Something about integration number 2. Maybe hit.
Yes, I will.
Thank you, and then I'll double check that one. Thank you. All right, if there isn't anything else, I've been stalling just for a minute to see if anyone wanted to form a question or anything. If not, we can finish the last couple of pages of notes. It's kind of an interesting note section too, I think, and it's not like not going to learn anything new. We're just going to talk about applying what we've learned in a couple interesting ways, ways that hopefully you might find interesting that you could imagine using in your own discipline if math isn't your discipline. And so, yeah, this particular section talks about applications of integrals, specifically to area and volume. We're going to focus on area and volume. There's lots of applications of integration. We're going to talk about just a couple here. And I like this particular page. I think I'm a visual learner, and so we're going to draw some pictures and get a handle on how this is going to work. And so, yeah, like it says here, there's lots and lots of applications. We're just going to talk about a couple of them, and let's draw a picture to sort of get the idea. So the idea, like it says in the prompt here, what happens if we want to find the area between two functions? Because we know integration finds area, right? Like in this last problem right here, this was a integration by parts problem, but it had bounds on it. And so we were finding the area between those 2 points under the curve, right? That's the whole point of integration, or one of the main points of integration, is to find area. And so what if we want to find the area between 2 curves? And we'll see there's an interesting application for this. So let's draw a picture. Let's say that one function does this, and let's say the other function does this. It doesn't really matter what you draw. Just try to make them intersect. And let's call the bottom one the function g, and we'll call the top one the function f. And we're going to figure out the area trapped between them from between 2 points. So let's throw 2 points on there. Let's say the first point is like their intersection point. And let's just pick some other random second point. And so, the idea is we want to figure out this area that I'm about to shade in. And I want to have that graph also on these other 2 plots here. So I'm going to use the magic of my iPad and copy these 2 graphs over there. But I would encourage you to just use, if you're doing this by hand, assuming, copy, try to draw the same picture 3 times. Let's make this a little bit smaller. All right, just going to pause and make sure everyone's got that same thing drawn 3 times. And so I'll start noting in a second. So the top one is sort of the finished product, and then we're going to note some things on the bottom 2 to help us understand how we obtain the one on the top. Okay, so you want to have the same graph drawn 3 times. And again, the idea is we want the area between them. Let's call that area A, capital A. Right. And so what we've learned so far is how to find area between graphs and x-axes. And so if we want it between the 2 plots, we can use that concept basically if we just kind of think carefully about that. Right, other questions about sort of the idea at all, what we're trying to do here before I keep going? Okay. And so the idea then is we would want to find all of the area between the 2. All of the area under F. So let me go ahead and delete some of these things here. We really want to find like all of this. Right, that would be all of the area under F. That's why I'm doing it in blue. And then we're going to subtract off what's under G. So we're going to subtract off this purple part that I'm adding in. Right, so just to be clear what I've just said in words, we want to take the blue area and then subtract off the purple. You with me on that? And if we did that, it would end up being what's between the 2 of them. Right? If we did that, we would get this. Just pause there and sort of see if people see what I'm saying there. Because we know how to do both those things, right? We know how to integrate and find the blue area. That's just the integration of F. And then we can subtract off the integration of G, which is going to be the purple area. And then if we did that, we would get what's between the two of them, which is what we actually wanted in the first place. Right, and this is our area A. Let me label it again. Because down below, we'll write an expression for what that area is. Let me see if there's sort of, do people pictorially see how that's going to work and what we're trying to get at there? And then if you're sort of, that does make sense, maybe think about in your head how do we write that mathematically? It's nice to have a picture, kind of think about what it means, then come up with the mathematics for it. Thoughts about the idea at all, though? What I'm trying to say there? So then it looks like this. All right, we can get it all on the screen actually at one time there, right? So A, the thing that I wrote down right above there, that area we want, is going to be the integration of G between those 2 points. Right, this is going to be the, oh, I mislabeled my 2 things. Darn it, I should have looked ahead at this. So I should have labeled FG and GF. Can we all switch that real quick? So I'm going to make my blue function G, and my purple function is going to be called F, just because it'll match what's down below there. Sorry about that, should have had a little more foresight. So the purple one's now F, and the blue one is now G. Sorry about that. And we want to do that because if you look at the definition down here, right, we want to take the blue area, right, the stuff that's under G, which is now hopefully properly labeled in your notes. I apologize for that. And then subtract off the purple area. And if we do that, we'd get what we've already sort of visually seen, we get what we want. But here's how it actually works. How do we go from here to here? Someone sort of help me with this. I've got 2 separate integrals, and then I've collapsed them into just one. Why are we able to do that? Any ideas? Have we seen that before, I guess is what I'm trying to say, or is this some kind of new thing that I'm seeing? So I think I'll just direct you back to, just want to show you where we've seen this before. Back when we first were looking at integrals and we looked at like integration properties, we looked at this idea. I'm going to highlight it in red here. Right, that said, hey, when we've got 2 things added inside an integral, we can split it up. And we use that property basically anytime we did an integral, right? You just like, it says you can look at the individual things separately, is what that property said. But that also means if you have separate things, you can combine them into one, right? And so we're kind of like going backwards on that property. And I just wanted to point that out because oftentimes we see properties like this and we're so focused on going forward like this way, where we're always going from the left side to the right side for so long that we lose track of like, oh yeah, if we have it on the right side, which is what we're starting with here, we could actually go back to the left. And sometimes it's helpful to do that. Right, so knowing, just having like a full understanding of what the property is telling us is all I'm trying to say there. Can I clarify that? See what I'm saying there? And so that's what we're doing. Let me just slide back down to the problem we're on then. That's really what's going on here when I'm saying, well, instead of doing these 2 things separately, we instead can do them, we can combine them together. And we'll see that it's potentially easier to do it this way. And then the last thing I'll just point out, it also says, but we need to make sure that G is the bigger function. This is the thing I missed before I labeled it, right? This is telling us which function's on top. We need to have the top function minus the bottom function. And that's important because if you lose track of that, you might subtract the wrong things, right? So this, in other words, it tells us which function to subtract. Okay, People kind of get the idea here. We're going to look at a couple kind of simple examples, but then there's a few things in the homework, one of those bonus things, whatever, one of the homeworks has some of these problems in there. Anything I can clarify there? Seems okay. All right, so let's look at an example. We're going to look at basically the same example twice. So the same two functions are in both of these two things, right? But we're going to look on different intervals, right? So 0 to 2 and then 2 to 10. And so let's do the same thing again to start here where we draw the same graph twice. Maybe in the future I should just put this on the piece of paper. So anyway, x squared plus 10 and 2x plus 10. So x squared plus 10 kind of looks like this. Really general ugly version of that. And then 2x plus 10 kind of is a straight line that cuts through it and makes an area. We'll see. It makes something we can find the area of. It does kind of like this thing. Except let me draw that a little bit better so we can have more something better to look at. Just a real rough idea of what's going on here. I'd like to actually continue this line a little bit. Okay. And the reason I chose these numbers, 0 to 2 and then 2 to 10, is because those happen to be those intersection points. And so I'll just kind of make that note up here. It's like if you wanted to know where those two things intersected, you would set them equal to each other. Right? If you take the two equations and you just make them equal, you're going to figure out the x values that make them the same, right? And so if you solve that equation, you would end up with x equals 0 and x equals 2. And so that's why I'm choosing those points. Just to be clear, it's like I'm choosing the point here where they first intersect, and then I'm choosing the other point out here where they second intersect. See that? And so I'm going to copy and paste this graph onto both pictures. You should try to draw the same graph twice. Let me just sort of pause there and see if everyone's on board with what we're doing here. Except I've mislabeled it. It should be 0 to 2 and then 2 to 10. So this is the 2 part. Sorry about that. And then 10 is like further out here, maybe like here, say. And so, on the first piece, we're trying to get in between the two of them, right? 0 to 2. And on the second piece, we want to get the other part out here. Right, so in both these cases, the sort of the red squiggly is the area we want. All right, I'm just going to pause there and see if people are on board with kind of the picture, the idea of the area we want. Are there any questions about either of those two things? What do you think? It's the reason I'm kind of doing this, and hopefully you can see based on the pictures. If there aren't questions about the pictures, let me know if there are. But is because in the first piece, in the top one, the purple graph is on top of the blue graph in the area, right? Like if I zoom in here, the purple one is on top of the blue. But if I look at this piece, the blue one is the one that's on top of the purple. And so that changes which one is going to be subtracted based on this thing that we just set up here. Right, this thing right here just said we need to be careful about which one we subtract because we need to make sure the one on the top is first and then we subtract the one on the bottom. Just to kind of make it even more clear, if I was going to look at, if I want that red area, I want to do all of the purple area, which is going to be way too much, but then you subtract off the blue area, which I'm now filling in. So if I do all of the purple, subtract off the blue, it'd be the red, right? So purple minus blue, so 1 on the top. That's what I'm trying to say. Thoughts about what I'm trying to say? I'm going to make a couple notes about that just in case it's not clear, in case people want to pop in with a question. But on this first one, I'm trying to say the straight line is bigger than the x squared graph on this piece, right? But on the second piece, the x squared graph is the bigger one. And so that determines what gets subtracted where. That's all I'm trying to say. So maybe in your head, think about what would those integrals look like, right? Based on the definition that's right up above here. Try to get it all on the page there. What's that going to be? Integral of what minus what from what to what? Right, take 1 second and sort of think about it. Maybe I'll just do the first one kind of slow and then give you a second to think about the second one. Right, so on the first one, the area, if this is our A in the middle there, it's going to be the integral from 0 to 2 of the one on the top, 2x plus 10, minus the one on the bottom, x squared plus 10, dx. And, you know, we want to be careful about that minus sign. We need to distribute that minus sign. But otherwise, this is a pretty easy problem now, right? It's just going to be kind of anti-power rule. And we'll be able to figure out that area between the two of them. Right, so I'll go ahead and finish that one just for completeness. So this is going to be the integral of 0 to 2. The 10s are actually going to cancel because we'll have 10 minus 10. So then we'll have 2x minus x squared, right? And that's really easy to do. That's just going to be x squared because you divide by 2 and it cancels the 2 out, minus x cubed over 3 from 0 to 2. And that's really easy to do too. It's 4 minus 8/3 because the 0, 1 just makes it go away, which is approximately 1 1/3. Right, thoughts on that idea? Let me sort of pause there and get rid of this thing too. I should have done that a while ago. There we go. Questions all? Is that okay? So hopefully you can see the next one's like the same thing. You just switch the order of the way that they're subtracted. And so maybe take a second and write down that integral. And also think to yourself, just looking at the picture, maybe thinking about the shapes of these things. I didn't do a great job of drawing how accurate that is, but just looking at the pictures that I drew, which area do you think is going to be bigger? You get 1.3 for the first one. Looks like that second one's going to be bigger or smaller. Thoughts about that? Which one do you think is going to be bigger?
The second one.
Yeah, the second one definitely looks like they're going to be bigger, right? The two functions are like moving away from each other. And so it's going to be this kind of larger space that we're capturing. So yeah, just kind of practically, it looks like that'd be the bigger one. But let's do it. So we just literally just switch this, right? So it'll be x squared plus 10 because that's the one on top, minus 2x plus 10 because that's the one on bottom. Just to be clear, this one went over here, this one went over here. I mean, the antiderivative ends up being very similar too, because it's just the same functions, there's just a negative in a different place. So anyway, it ends up being like this, right? So we'll have X cubed over 3 minus x squared from 2 to 10. Now this one actually takes some work because they're not just equal. And so this is going to be 10 cubed over 3 minus 100. 2 cubed over 3 minus 4. And ends up being a lot bigger, 235. All right, so compared to 1, a lot bigger. All right. It's not, not the hardest idea. Hopefully you can kind of see what's going on. No one's asked any questions. That's not too surprising, but hope that's just because it kind of makes sense. We're going to see how this gets applied on the next page in kind of an interesting way. But before we do that, I'm going to kind of challenge you with one to see if it makes sense or not. But are there questions about either of these? So there's a couple in the homework that look like this. And again, this is more of a challenge one, I would say, just because it makes you think. It's not exactly like the last couple we did. It gives you more of an idea of how you might see this. And then we'll see it get applied in this application down there. But anyway, let me sort of draw the picture here and ask you to think about how this one's going to work. So we're going to find the area bounded by the natural log and a straight line, kind of a random straight line with a slope of 5/7, and the x-axis. So let's draw the picture. So let's make ln purple. ln just kind of does that slowly increasing thing, right? It does this. And we'll make the straight line blue. And that straight line you can see has an intercept of -5, and then it's going to come up and intersect the ln. And so it kind of does this sort of thing. You know what? I'm going to just make an actual straight line. That's pretty good. Yeah, pretty much looks very similar to that. Okay. And so what we want, it says the area bounded between those two things, but also and the x-axis. Let me actually just make ln just keep going, just so you remember it keeps going that way. And so we want this area in here, which maybe on first look is like, oh, well, that's not so bad. That's kind of like what we just did a second ago, except we want to avoid the area that's below the x-axis. So we're trying to avoid this part. So we don't want that to be included in whatever we do. Gosh, my pens, there we go. Okay. And so I want you to take a second and think about what that integral would look like, but let me go ahead and label the x values. So does anyone know where ln comes and touches the x-axis? Where's the x-intercept? Remember that? This point right here? Didn't remember that one? That's ln equals 0 when x is the number 1. So that's the first point we'd be concerned about. The point where the blue curve touches the axis, we would just set the line equal to 0, and we could figure out that that's 7. And then the second point is a little bit more tricky to figure out. It's where the natural log intersects the line, and I'll just tell you it's approximately 10.26. So take a second and think about what would the integral be. All right, this is the area A we want. Make that a little thicker. All right, this is A. What would we write down as an integral? It's a little bit trickier. Again, remember when you write down like integration a to b, you're finding the area between the function and the curve. And so we're going to have to think a little bit about how this one works. Just take a moment and think about that one for a second. And I can happy to clarify something if someone wants to speak up. Any ideas?
So would it be from like 1 to 10.26?
Of what function?
ln x.
I like that. So we're going to do 1 to 10.26 of ln x. But if we did that, just to be clear, that would be all of this area I'll do in black. That would be include all this stuff over here too, right? It would be all of that. And so what do we need to add to this to sort of fix it? Right, we want to get rid of this piece. Anyone? See what I'm saying? So what Jorge, I think Jorge, yeah. I'm sorry, say it again.
Minus 5 over 7x minus 5. Is that what it would be?
Yep, between what 2 points?
The same, I would assume.
So this is where the thing we want to avoid is. That was a good thought. So I was
Could
just
it be between 7 and 10.26?
Yeah, we just want the part from 10 to 10.26. So we want, we want the chart I've shaded it in black. We want to subtract off the part I've shaded in yellow. And so the black part corresponds to the black integral so far, right? So this black part right here is this integral, right? And then the yellow part would be just from 7 to 10. If we went from 1 to 10, like was initially suggested, we'd end up
with that blank space.
With this blank space that we're trying to avoid. Yeah, and it would actually be a negative blank space, and so it would be this weird thing that would happen. And so let me erase those two things. And yeah, so then we want to subtract, oops, let me make that a little thinner. Subtract off, oh, this is a dx situation, minus the integral from just 7 to 10.26 of the straight line. Just sort of pause there. So the thing I would just highlight, maybe I'll just sort of box it in too so it stands out a little bit. The top bound stays the same, right? Because we're sweeping across that whole area, but the bottom bound changed. Because we don't want that first part. So in other words, when the x-axis gets involved, it just takes a little bit more time to think about. And some of them in the homework involve the x-axis. Thoughts about that at all? Write down the solution in just a second, but this is I'd say the tricky part. Actually, this one does get a little bit more tricky. Thoughts though at all? Does anyone know why I'm saying this one's tricky? Because now we want to do this. Which one of these pieces is a tricky one? Does anyone remember this from last time? This one actually ends up being the ln is an integration by parts question. We did this one last class, right? ln x is one of the last ones we did right here. And we did all this work for it. Wasn't too horrible, but it involved one of the sort of advanced integration techniques. And so I'm not going to do it again. You can note up here that it ended up being this. I'm sorry, ended up being this. And so I'm going to kind of just skip down to that solution. If you want to double check the work, you can double check up there. So we did this integration by parts. See above for work, for details. But when we want to finish one off, we do integration by parts, and it ends up being x ln x minus x from 1 to 10.26. That's the part that I'm skipping over that you can look above if you want to see the details. And then the second part is not hard. That's just an anti-power rule kind of thing, right? It'd be add 1 to the power, divide by the power, right? Add 1 to the power. Second part is just sort of a normal kind of integration. And if you did all that out, I'm running out of space here, but if you plug the numbers in, do the subtraction, all those things, you end up with 9.8, about 9.8. All right, hopefully you kind of get the idea there, how that kind of works. We're just going to finish off this class, finish off the material here with an interesting application of this, something that may not look like it's this kind of thing at first, but we'll draw a picture and we'll show exactly what's going on there. Anything I can clarify though? All right, let's look at an example of this. So I know there's a lot of words on this next page, but I'm just trying to remind you of something and sort of connect the dots before we look at this actual example right there. I'm just sort of trying to remind you that, remember that when we write down something like that, when we write down the integral and we write bounds between it, previously just talking about is doing area, but when it was originally introduced, it's like doing the total amounts of the function between those 2 points. That's how I originally introduced it. It's like we want to add up total amounts of something, right? And so that is how we do it. And one particular application that comes up a lot in sciences or modeling, or like infectious disease modeling, for example, when people talk about coronavirus and things, is if we have a rate of change and we integrate the rate of change, that tells us the total change, right? And so, derivatives are rates of change. And so what I'm saying is if we add up a total rates of change between 2 points, we get the total change between those 2 points. For example, let me just kind of bring it back to a common thing we've seen throughout the course. Excuse me. We'll look at a more specific example below, but let's, all throughout the course, we've been looking at this function C prime of t, where C prime is the change in concentration of some drug. I always had this like hypothetical drug function I kept coming back to. We called it C, or C prime. And so let's say this is change the concentration of a drug in your bloodstream is what we had originally said. And so in that case, if we integrated this thing between 2 points, it would tell us the total change in concentration, right? So if this was like Advil, we took it between 2 points, we wanted to know how much is in our bloodstream by this point, and we had this function, we could integrate it, right? That would tell us the total change in concentration. And so that's a kind of, you can kind of imagine where that becomes useful, right? Patients taking a drug, how much have they ingested? Do you need to give them more? You just need to wait longer? That's the kind of question you need to think about, right? Maybe if it's like a morphine dose and a patient's in a lot of pain, is it that they need more morphine, or is it that you haven't integrated far enough, right? You need the time to go longer so that they have more concentration. That's the kind of thing that people think about in these types of applications. And so I made up this other application. Yeah, I don't think I took this one out of the textbook. I think I came up with the idea from a textbook, but I just made up the functions so that they were kind of easy to deal with. But let's look at the change between 2 rates. And so let's say, and I'll draw a picture to go along with the second example. Let me zoom out a little bit to draw this picture. Let's say we've got this lake. Or pond or some body of water. And the idea is that there's like pollution entering it from one direction, or from some source. It could be there's boats that drive in it that drop pollution, or maybe there's a local sewer that's broken, that's leaking into the lake. Whatever it is, it's being polluted at some rate. Let's make the pollution red because pollution's bad. Right, so P prime is coming into the lake. and P stands for pollution. And then, so what, one thing that people do in these situations is they'll try to filter out the pollution as it comes in. If they don't know where it's coming from, for example, they'll just try to filter it out. And sometimes you see this in the form of like grates in the lake. You ever see that? And there's like water going into the grate and it's kind of filtering things out. It's like a giant filter for a fish tank. And so let's say there's a filter rate, F prime. And we have an equation for both these things, right? So I've boxed the purple equation in. That's how much is being filtered out. And so it's being filtered out at a constant rate, right? Just like you run this filter and it's just going to filter at a constant rate. But the P prime equation is a negative exponential. Let me go ahead and zoom in. Hopefully people are caught up, right? And so if I kind of thought about what these two graphs looks like, this graph kind of does this sort of thing, the red graph, and the purple graph is a straight line. And so there's something interesting going on there where they intersect, because it's like at some point the pollution is going to be more than the filtering, but it kind of looks like the pollution is going to level off and maybe the filtering will eventually be bigger than the pollution intake. In other words, for a while, the pollution is going to get worse, but then at some point it's going to start getting better. Just kind of looking at the pictures that I drew there. And we can figure out answers to the kind of questions I just asked. When's the pollution going to go away? When's it going to start going down? When's it going to keep going up? Or the question that's being asked in this particular problem is, how much will there be after 12 hours, right? But there's lots of questions you can answer sort of this with this general idea, just using integration and the concepts we've learned in the course. So I'm just going to pause there and see if there are questions about the setup at all and let people finish drawing the pictures and whatnot. Questions at all? All right, well, using the concepts then, maybe you already can think about how much pollution exists after 12 hours, but to help sort of scaffold that idea, can someone tell me what happened, or what does this value give us? If I integrated the pollution rate from 0 to 12, because we want to know about 12 hours, right? What would that tell us? And maybe you can guess. The second question is going to be, what happens if you integrated the filtering rate from 0 to 12? What do those things tell us just by themselves? Anyone, you can say it, you could type it. Just think it yourself and hope someone else says it. I'd love to hear it. Yeah.
Would the first one just be like how dirty the water is after 12 hours?
Yeah, it's like if you integrate that rate and as a pollution rate, it's going to tell you the total gain or change in pollution. And in this case, it's going to be positive. Yeah, so it's going to be like the total pollution gained.
And then when we get the one for the filter at the bottom, what will we do with that? Would we just subtract that number to the other number?
Good question. So first of all, what's that one telling us? The purple one, it sounds like you know what it's telling us. We integrate
it's
the pollution.
telling us like the filtration rate. So like how clean the water would be.
It's going to tell us if F prime is telling us how much pollution is removed at a given time. If we integrate it, it's the total pollution that's filtered out. Assuming there's pollution to be filtered, right?
Mm-hmm.
And so then, the original question was how much pollution exists. And so what would be the total? This is, I think, Sebastian's question, is how do we put them together to figure out the net pollution? Some integral. Thoughts? Maybe Sebastian can finish it, or if someone else has another idea.
So would it be you integrate P of T and then F T?
I'm sorry, you cut out for a second. Integrate P and then what?
And then subtract, well, integrate F, but subtract it from P.
Yeah, I think you said that correctly, right? So you want to do the total pollution and then subtract off the filtering. And so it would be from 0 to 12, P prime minus F prime. I mean, technically, and it sounds like people are thinking about them separately. Yes, technically you could do them separately and then subtract them. But what I've set up here is if you have them separate, right, then you can combine them into one. And so I'm just kind of jumping right down to the combined version. Right, and that's not too bad of a problem in this case because we have an equation for each one and they're not terrible. It'd be 0 to 12 of the pollution one. And we can draw a picture in a second here. I'll have to go to the next page, but I'll draw a picture of this in a moment. Minus the filter one. I already kind of drew the pictures up there, but we'll combine them in a second. Right, we have rules for both these things. The 0.4 T1 is the anti-power rule. How do the E1? Let me actually rewrite it and then we'll think about that. I don't want to spend too much time on this unnecessarily, but it's good to help think about how we'd actually do this. Right, so this one's not too bad. That's just the anti-power rule. This one's just a constant rule, so that's just going to be 10T, right? How do we do the E part? Because it's not just a normal E, it's E raised to a function. Ideas? I think there was maybe one of those on the last test, if I'm not mistaken. E raised to a function. Anyone take a look at those solutions if you didn't get that? We can look at that test too. I forgot to mention at the start of class. We should probably look at that test a little bit. Ideas? What do we do that one? Saying something, Jorge? Maybe you're not. You're lighting up, but I don't hear it.
Trying to say something, but I don't know how to get it out. Would it be you add 1 to negative 0.5?
Nope. So it's not a power rule. So this one is a substitution method. Maybe we should we might want to revisit that one based on how people did in the last test. All right. So you would do. I'm not going to go through the details since I'm at the bottom of the page, but you do U equals minus 0.5 T etc. That's not really the point of this problem. We can look at those details if you want. The point that I'm trying to get out here is if you did this integration, if it's kind of clear, we know how to do it. We've learned techniques to do each piece is what I'm trying to say, even if it's a little fuzzy. We would get approximately 71.25. In this case, I think it's measured in gallons, right? Gallons of pollution. So I really just want to tie this into the thing we just learned, like the picture. So I'm going to throw another page on here, but let me see if there are questions about the concept. Pause there. Questions? Let me draw the picture. So let's draw a nice big picture, except I'm going to move it down. So we did pollution in red. That was this 1 minus E thing, which roughly actually ends up looking like a log when you graph it. Kind of does this kind of thing. That's the P prime, which is the pollution function. And then the filtering one is the straight line, and it actually ends up intersecting that and does this kind of thing. Let me move this over. Let me do have it better. Just totally rough sketches here. The point is, at one point, the pollution was higher, and then at another point, the filter ended up being on top. And the thing that we just looked at in the problem was 0 to 12. And so 0 to 12 was like somewhere in here. You know, we just did this in the last problem. And that's why it was a positive number, right? Because it's like a positive is above the x-axis, it's a positive area. But what I'm trying to point out here is we can see visually when the pollution is building, right? When there's sort of getting more pollution from time to time, right? And to be clear, the x-axis here is time. So we're going time on that way. And then at some point, it starts to go down. When does that happen? What am I trying to say here? At what point is the pollution going up? At what point is it starting to go down?
It switches when P prime equals F prime.
Yeah, exactly. Right. So this whole piece in here, where the pollution is bigger, we could describe that as the pollution is going up. It's building, right? Pollution's building. But then when they intersect, it's like, well, the filtering and the pollution rate are the exact same at that moment, right? This is P prime equals F prime. The two rates are the same. Whatever's going in is immediately being removed. And so that means that at the other side, the filtering's higher, right? And so the pollution is going to be going down in that point because the pollution, the rate is bigger than the intake. These are rates of change. So it's like what's going in versus what's coming out. And we can just visually see where that's going on. So in other words, if we started integrating this longer, we could start to see it going down. At some point, it might be 0. Anyway, that's sort of the idea. I think that's really all I wanted to say about that. Can I clarify anything there? All right, how are we doing on time here?
Are you ever gonna ask us to find the pollution going up, and then after you're gonna ask us to find the, or are you just gonna ask us like a conceptual question, like, okay, you just did all this math, is it gonna, which function is gonna be higher after this? Like
The
you
way
would
that
just
this
be
is-
like, oh no, you can go.
This is not, let me just remind you where this is going to be applied. So, you know, the final exam is all we got left and the homework that's due on Wednesday. And the homework is bonus. So the only place where this stuff shows up is in the bonus homework. And in the bonus homework, I think there are a couple of problems that ask you to actually do a couple of problems, like subtract this minus this in an integral and figure it out. But some of them are just conceptual, like you said. Like it literally like shows a graph, shades in a region, and just says, you know, and I think there might be multiple choice even, like which one of these choices represents the region that's being shown. I don't know if there are any, I can't recall if I put any or if there any existed. There were a few actually in there that were kind of like this, where it gave like a rate and it said like, oh, what if you integrated this rate between these points? Like, what does that tell us? But those are all the bonus problems. They're all bonus problems. So it's not something to stress over or trying to figure out what I'm going to ask so you can get the question right on the exam or something. Does that clarify it for you?
Yeah, that's smooth. Real question. Remember how we used to do like log, or not log, but like we used to do some at the beginning of the year. Logarithmic functions, right? Wasn't that what we were doing?
You mean limits?
Yeah, limits. That's how many problems on limits are about to be on the final?
Like 2,500.
I like it. All right, definitely got to crack open them books. Hell yeah.
Yeah, I was actually just looking through the final I gave and I was trying to get it ready and stuff. And I'll remind you that we saw limits twice, is what I was reminded of when I was looking through it, right? We saw limits early on that we learned techniques about. Let me just sort of pause there. I'm happy to sort of transition and start talking about the final or anything else you want to talk about. Are there other questions about this page or anything before I move on? Okay, so I don't want, come on, where's that scrolly thing? I hate when it does that. Anyway, we learned about limits way back in the beginning, and I guess I can just scroll up there, which is what Sebastian's a little bit concerned about, sounds like.
Man, I'm not concerned. I just want to know how much I should have to look back at it.
Okay. Now, let me try to clarify that a little bit. So there are these 3 techniques we learned about. That was part of the first test. Hopefully you had some stuff on a note card about that for the first test. You could bring that in and use it. And, you know, there's plenty of examples, both the notes and practice problems and the test itself that have these types of problems. I may ask a couple of them. Is it going to be 5 questions or something? No, absolutely not. But the thing I'll remind you is not only did we see limits here, but we just saw limits like right before integration too. Do you know what I'm talking about?
With like L-Hop's rule.
Yeah, L-Hobbs rule, exactly. And so let me just sort of show you that real quick. And so what I've done on the past, which maybe you like it or maybe you don't, is to say here a couple limits, just a couple. Here's L'Hopital's rule, right? It gives here's how we actually do it. I'll give like 2 or 3 limits and say use either the techniques from the beginning that I showed you a second ago, or L'Hopital's rule to do these couple problems. So in other words, instead of breaking them up and seeing it twice on the test, it'll just be like one part of the test, couple problems, use either techniques, any technique. What else do you want to hear about? I know we're at time. You're welcome to go if you want. I was going to sort of do a 50-minute class, so happy to bounce out of here if you want, but I'm happy to look at whatever you need help with as well. If you want to start talking about final, homework, other questions like that.
Are you hosting a review session tomorrow alongside the one that's going on Wednesday?
A review session tomorrow? I don't have anything planned for tomorrow. No.
I know. I just made it up right now. I'm kind of baiting you into it.
Is that you asking to do that? Speaking of which, I have to double check my schedule. If I remember correctly, I think I got my schedule like crazy booked up tomorrow, and I may have to move office hours. But yeah, if you wanted to do you want to do something in the evening? Let me look at my schedule real quick here.
I mean, like we could host something in the evening tomorrow and then host something again like in the morning or in the evening on Thursday. That way it's like a 3-day just back to like you could genuinely break it down like first test tomorrow, second test Wednesday, third test since it's the most recent on Thursday. That way you get the breakdown. And whoever want to show up to whatever session is going to be there, right? For this specific like situation, whichever one they want to review the most.
Here's the thing. I already have a bunch of evening review sessions for other classes.
Oh. So this calc class not that important, huh, Mr. Levy, huh?
Well, they were a little more proactive about pestering me to schedule those things. So we could do, I mean, what time tomorrow? I'm going to be driving home tomorrow. I could do tomorrow. Are people really going to be studying tomorrow? I feel like it's too early. I don't want to do this like.
Nah. Temp came with me. Me and Josh are on the same boat. I think we all feel the same. We want all 3 sessions. We trying to get all 3 tests, trying to see everything, all the materials. Because on the final, he talk about, this about to be like a couple rules on limits. You can use whichever one. You're going to have to use every single formula in there to just answer the question.
I don't know what you're talking about, but here's what we can do. We can spend all class on Wednesday for sure. So if you're really dying for these sessions, take advantage of that.
Mm-hmm.
Do we want to put something in? God, I really don't want to come here tomorrow night and no one show up. Can we do Could you do tomorrow at like 9 p.m.?
That's fine. We don't sleep. We
That
children.
works. That works for me.
Yeah, we children. We don't sleep. As long as you willing to be awake, that's fine.
Let's start there. Tomorrow night and then Wednesday during class. If no one comes tomorrow night, that'll be the last time. I'll tell you that right now.
Nah, don't worry. I got you. I'll put it on my life. I'll be there. 9 o'clock. 9 o'clock. We're gonna be
Alright,
there.
yeah.
We gonna be doing not log limits. We're gonna be doing limits in there. It's gonna be a whole lot of limit work.
All right.
And whatever else. A whole lot of it.
Anything else? What else you guys want to talk about? All right, will I just see you tomorrow at 9 p.m.? Can't believe I just signed myself up for that.
Yeah, you kind of just set yourself up for 3 extra work sessions, but let's go, Mr. Levy. I know you want to do it because you're a good teacher. I know you want to do it. That's why you're gonna do it. But yeah, don't cry. We're gonna bring tissues on Friday. We're gonna make sure that when we leave, you're not crying too much. Make sure you're good, you're feeling good. You're gonna walk out of here like these is the dumbest kids I've ever taught ever. They definitely tried though. I feel like that's how you gonna feel.
All right, it's time to stop this recording.